Greetings and welcome back to a new video. In this video I will like to discuss the state space modeling, which is a very important topic in controller design and control systems, specifically when we talk about the modern controller design. We have dealt so far with the, let's say, the old classical way of designing controllers, and this topic is way towards the modern controller design. In this video I will discuss the modeling of that, so the modeling of the systems, let's say an electrical system or a mechanical system, so we will dive into details of that. And once we have done this video, we will discuss in a separate videos also the design of the controllers for a specific dynamic system. So let's start and also discuss our outline for this video. So we have several things to discuss. We have a theory. So we will start, for example, first with the general state space representation and then apply this. And we also give several examples as shown here. We have example 2.1 up to 5.1. So we have 5 examples and I've also listed them here on the right side. So we have a discussion and in between we have several examples to illustrate the concept and then we move on. And I hope this complete picture will give you a nice summary of our state space modeling discussion. So let's move on. We have the first topic, which is our general state space representation. So let's first discuss what it is. And before we move on, let's also talk about the linear systems or linear combination of systems. And what is a linear combination? It's composed of linear combination of n variables. We can call it an xi with an index I, which runs from 1 to some number n. And it has a constant coefficient. So if I now write it down as a summation, you can write it in this form. So summation of I is equal to 1 up to n in integer format. And we have this summation. If you work it out, you can go up to a1x1 up to anxn, which is some number. Now you can have now the state variables. Now what is that in precise form? That it is the smallest set of variables in your system. And it includes also the input signals and also your model of your system, so the dynamics of your system. So we have the input and also dynamics. So in, let's say in a pictorial view, you can say this is the dynamic system we're talking about. And we have the initial conditions given by x at 0. And we have the input. And of course, we will have some output due to those two inputs. Okay, now it provides the information about the current state. We already discussed that because we set the initial condition and the future states. So after, let's say, t0 at some specific initial time of the output. It is, by the way, not limited to physical systems. It can be also in a biological system or an economical problem or even social and any other systems you can actually imagine. Of course, we will discuss mainly and consider mainly physical systems like the mass damper spring or RLC circuit, because we are most often interested in engineering systems, but this can be extended to many other systems. So what is a state space? Let's also discuss that because we have now discussed the state variables. Let's move on to the state space. Now, it is a state and it has a space, so it is a combination of these two. So we can have a picture here. The x1 and x2 are represented our states. So we have now two states here, just to imagine this in 2D. And this is the space we are talking about. What we have is this vector, which is the state vector. So we have state variables, and this state vector is the effect of this x1 and x2. If you have, of course, 3 variables, you will have another vector, which is then dependent by 3 state variables, which are x1 and x2, and also x3, for example. Now you have this vector that will have some trajectory, so they will go in specific path. At, let's say, beginning, it has this position, so the length and also the, let's say, the angle. but at some specific time later, it can be here. And then we have this path. And in this case, you also create a space. So this is sort of a pictorial view what a state space is. So it has the axis, which is the x1 and x2. Those are the state variables. And the space is formed by this state vector. And the state vector maps that state space, as discussed earlier. This was just a general view. Now, if we now talk about the state's representation of a dynamic system, let's discuss this in this pictorial view. We know, and we have discussed in various videos, and used block diagram representation. Now, state spaces consider multiple, let's say, feedback elements. So that's why we have, let's say, these arrows here in this particular format. Now, what you also see is, this is an interesting thing, the D here, which is actually from this command input, goes directly to the output. So that means actually direct transfer without any, let's say, path through the complete dynamics of our system. Now, this whole expression has 4 matrices, A, the B, the C, and the D. And the D is the forward transfer, the B is the D, and the A is the feedback element, which is actually sort of the dynamics in our system. And the B is also from going, let's say, the forward path, going directly from the U to this summation point, and the C is the matrix going from the state vector to the output. Now, this all together can be represented in this state space expression, where we have the x dot. Dot means actually a time derivative, so 1 dot means a first time derivative, second dot, so 2 dots means the second time derivative. In a similar case, we have this for the y. Okay, now this state vector here, which is already set, and the x dot is a time derivative of that state vector. We have also the output vector, which is y, and we have also the u, which is called the control vector, but can be also just a unit input vector. And we have the matrices A, B, and C, D. This is the system vector, system matrix, I mean. This is the input matrix, so going directly from the input to the summation point. The C is called the output and matrix, and the D is the feed forward or direct transfer matrix. Okay, let's now look at applying the state space representation, because we have several things to do before we can do that. So the selection of the state vector. So minimum number of state variables must be selected as components of the state vector X. So you need to first determine how much state variables you need, minimum number, and that is then the, let's say that those are the components of our state vector. As in the linear algebra, we have a vector that has its own components. Of course, we need to discuss this later in great detail. What are the minimum numbers? And it has actually a link, direct link with the order of my dynamic system. So the minimum order of your state variables is sufficient to describe completely your state of your system. Again, if that is sufficient. Components of the state vector must be linearly independent. It's very important. We talk about state space, and we can only do that when we have linear system or linearized system. That is very important, because we talk about linear operations as we do in linear algebra using matrices and vectors, because that's all the business also here. We need to have linear operations and linear systems. Okay, now linear independent state variables, what does it mean? Now, independent summation. For example, if we have x1, x2, x3, and x4, so 4 state variables, we have chosen that from our dynamic system. And we know that x4 is given, let's say, by x1 plus 4 times x2 minus x3. And what does it mean? This means the following. x4 is not linearly independent of x1, x2, and x3 because we can make x4 using the other three state variables. So this is actually not a good choice for our state variables in this case. So we need independent summation. Also, what we need is independent successive derivatives. So this is, let's say in this example, the current through a capacitor as a time derivative. So the capacitor current is equal to the capacitor, the capacity value of this capacitor times the time derivative of the capacitor voltage. Very standard formula in electrical engineering. The current through a capacitor is linearly independent of the voltage across the capacitor. You can see that. It is linearly independent of the voltage across the capacitor. But the capacitor current IC cannot be evaluated as a linear combination of the capacitor voltage. So that's also very important here. So the minimum number of state variables here, and that is given by the order, as we said before, for your differential equation describing your system. Let's say we have a mass damper spring system. It has a second order differential equation. We need two, because it is second order, two state variables. If you have a fourth order system, you need four state variables. That is how it's actually determined. For example, as said before, for a fourth order system, we need four simultaneous first order differential equations. And this is one of the, let's say, advantages of using a state space format. Because where you have a fourth order system, you can decompose that in four simultaneously first order differential equations. So we actually make first order differential equations from, let's say, a fourth order system by decomposing that in four simultaneous systems, along of course with your state variable. So you choose that. So if you have a 10th order, you will have 10 simultaneously first order differential equations. This is also very important and helpful in different systems. You have the number of independent energy storage elements in the system. Now let's also give an example on that. For example, in an RLC circuit, electric circuit, we have two energy storage elements. The R is not a storing element, so it is in theory, in ideal case, just a resistive or dissipating element. But the inductor can store magnetic energy, and the capacitor can store electrical energy. So it has two energy storage elements, L, the inductor, and the C. That means we know that, of course, from experience and all, maybe from other examples, that this is a second order system. We have second order system, that means we have two state variables also here. As said, second order system, so we need two state variables and also two state equations. But if you have, for example, an RC circuit, then you have only first order system and you will have only one state equation. But if you have a RC circuit in cascade with another RC circuit and another RC circuit in cascade, so let's say 4 or 3 RC circuits in cascade, then you will have maybe fourth or third order system, and you have again 3 or 4 state variables required for that. Really depending on the order of your differential equation of your system. That's actually the key point here. Okay, so if there are too few state variables selected, it might be not possible to write the particular output equations. Since some system variables cannot be written as a linear combination of the reduced number of state variables. So we have reduced actually our state variables from, let's say, 4 to 3. And it might be the case that you cannot express the output equations in a particular form. That is, let's say, the condition here. So we need to have the minimum number of state variables. Okay. Let's give an example. I think we have discussed enough material so far, so let's move on and also discuss an example here. So we have an RLC circuit here. You can see the inductor in series, the parallel combination of your resistor and the capacitor. We see the inductor current IL, IR for the resistor, the current, and the capacitor current also here. And we have also the capacitor voltage shown here. Vs is a voltage applied here. All of them are time dependent. So what we want is the following. Given this electric circuit or LC circuit, determine that a state space representation if the output is the resistor current. This is important because I can give you any other system, mechanical, thermal, whatever it is. If I don't mention the output, you cannot actually determine the state space representation. So I need to also mention that clearly. We have an input, Vs, that's the voltage, and we have an output, IR, that's the current through the resistor R. So we have now enough information. Let's then work out the solutions. Step 1 is select the state variables by writing the derivative equation for all energy storage elements. Again, we've discussed this. Inductor and the capacitor are the two elements that will store energy. So we can say for the inductor, let's then write down the equation, the physical equation for that in a derivative form, which is then L times the time derivative of its current is equal to the voltage across that inductor. This is again a really standard physical formula. Let's call this equation 1. We will need this later. Now for the capacitor we have again the capacitor current, the C, the capacitor capacity here, times the time derivative of its voltage across it is equal to the current through it in time dependent fashion. Okay, we have now the step 1, and that's then equation number 2. Now choose the state variables as the quantities that are differentiated. Let's look at equation number 1 and 2. What is differentiated? It is the inductor current that is differentiated, and it's also the capacitor voltage. Now we can say, aha, the state variables are the inductor current and the capacitor voltage. It's really that simple if you just follow the step here. Okay, now step 3 is express the, let's say, the non-state variables. So we have the state variables IL and VC, but the non-state variables are VL and the IC. So we haven't chosen that as the state variables. Now we need to express the non-state variables, these two, as a linear combination of the state variables we have chosen and also the input. That's also important because we have also the Vs. We don't forget that, of course. All right, now let's call this point P because we need to work out a little bit more equations here because we need to use now the governing equations for the circuit, which is let's say the Ohm's law, Kirchhoff current law, voltage law at point P. And I will just apply direct the nodal analysis here. We can say, okay, this current will split in this and this current. So IL is equal to IR plus IC. That's actually shown here. And it's also one of the things you need to know before you can work out these kind of, let's say, systems or circuits. You need to, of course, also know the laws governing your system. In this case, we need to have the Kirchhoff current law. Okay, moving on, IL is shown here, and IR and IC. Now, I can also write this in this form, so I can say IC is IL minus IR. Why do I do that? Because I want to have the expression for the non-state variables. This is one of them. Of course, we need to move on and look at IL and IR also. We know from Ohm's law that the voltage across a resistor divided by its resistor is also its current. So we can now replace this, and it is here. Why do I do that? You might ask, why do you do this? Because I want to express the IC in terms of the state variables, which are IL and VC. It's already given in one of the state variables, IL, but not yet another one, which is VC, so I need to convert this. That is actually shown here. Of course, this voltage is parallel to that voltage, so it's, of course, this capacitor voltage is exact same as the resistor voltage because those are parallel. That's the reason, and we have now the expression for the IC, one of the non-state variables, as a linear combination of the state variables, which is what we required. And let's call this equation number 3. Now, using Kirchhoff's voltage law, so in this case another law of Kirchhoff, around the outer loop, which is actually this loop, going like that. Yeah, the complete loop. That is just the voltage here, Vs, we apply, that's equal to this voltage across the inductor, plus the voltage across the capacitor, or across the resistor, whatever you prefer. Again, we need to select the VL as our non-state variable and express that in IL and VC. Let's see what we can do. Now we have, and also the input. Now we have already something. And we have also the input, so we can say, okay, this is already fine. So we can just say this is equation number 4, because we have the input, and we have this one of the state variables, which is the VC. All right, we have now developed our equations in step 3, equation number 3, and also equation number 4. Now moving on to step 4, what it's actually saying is the following. Now we have 4 equations now. Of course, we need to have 2 first order differential equations, because we have 2 energy storage elements, we have a second order system, and we need to make from the one second order system 2 first order systems, or 2 first order differential equation expressions. That's actually the whole business. Now in order to do that, we can substitute 3, this one, in 2, because you can see IC is going here, and we can substitute 4 in 1. Now let's do that. This is for the first case. So in this case, we just moving this one. You can see this is a first order differential equation having only your state variables VC and IL. Very nice. And that can be also rewritten in this form, so you can divide the left and the right hand side of this equation like that by C, and you have this expression, which is also what you need to do in a final form. Now let's also do 4 into 1, and you get this. So we have this, and the VL, and VL is this one. Okay. Now when we move on, and we again want to have an expression here, just that state variable differentiated, we can divide left and right hand side by L, and we have this expression. So we have now actually a complete expression for our input state variables VC and IL. Now the final one is of course our output, so determine the output equation. That is the current through the resistor. That's actually straightforward. Again, as said before, the voltage across it divided by its resistor using Ohm's law, but we know that it is also the capacitor voltage, so we can just say capacitor voltage over the R, and that is actually for step 5. Okay, now we have everything. And that's now equation number 5. Now let's collect them, and this is our input state variables, state variables equations, these two, the red and the blue one, and the green one is our output equation for the current through the resistor R. Now step 6 is actually use now the standard state space model. That's the following step. This is the state space model we have discussed. We know that this is the U, which is our command input Vs, and the output Y, which is our current here through the resistor R. And this is now again our state space equations. The first derivative, time derivative of the x is equal to ax plus bu, and also the output is given by the cx plus du. Again, the d and the c and a and the b are discussed before. So a is the system matrix, b is the input matrix, c is the output matrix, and the d is the feed forward or the direct transfer matrix. Okay. Now the next step is let's define a state vector. We already have the state variables, which is the inductor current, also the capacitor voltage. We know that. But let's also make a state vector that is straightforward by actually setting in a vector, just x in this case. You can also call it different, give it a different name. And you have then the first one, let's say VC, and the other one is IL. But you can also say IL and VC. So we have a vector with two, let's say, coefficients or two elements in it. if you now do the time derivative of that one, so there's a shorthand notation for the time derivative of that state vector, then you differentiate actually the VC and also the inductor current. Why do we do that? Because we have that also in our expressions here. And that's the reason for doing that, and we have already a sort of standard. Now if I now differentiate this, so we have the x dot is differentiated here is equal to some matrix, which is our system matrix A here, is also shown here, times the state vector plus some matrix or vector, actually in most cases B, times the input, and that's actually U and a B here. So this is still empty, so we need to fill that in. So if I do that, there will be this. You can say, okay, how is that happening? Now let's check that, because the first time derivative of that capacitor voltage is equal to, is actually shown here, 1 over C times that inductor current minus 1 over RC times the capacitor voltage. Now if the capacitor voltage is up and then the IL is down, in this case in the format, and we know from linear algebra for multiplication of matrices using vectors, we know this must be multiplied by the first element here, and this one must be multiplied by the second element of our vector. So this one must be multiplied by minus 1 over RC. That's actually shown here. And 1 over C must be multiplied by IL. It's also shown here. So we can now just locate actually what this element must be in our matrix. This is just a 2 by 2 matrix. Of course, we have a second order system. If you have a 3 by 3 matrix, you will have a third order system. Now let's also check the DIL dt, so the time derivative of that inductor current in a similar form, minus 1 over L times VC, and then 0 times, because there is no IL here, and that is actually the let's say this element. There is an input here, so it is 1 over L, but there is no input in this expression, so we have the 0 there. So 0 and a 1 over L. And then that's actually the expression for the state space for this part, first part. So the A, the system matrix, and also the B, input matrix or the vector. All right. Let's also look at the output, because we have also an output expression Y, which is now in this case just a current through the resistor. We have an element here, and we also have an element there, so the value here. And we know it is VC over R, or 1 over R times VC, shown here. And there is no IL in that expression, so 0 times that. So this is just the C matrix shown here. And there is no direct transfer. How do we know that? Because there is no direct connection from the input to the output. It must be then, let's say, a connection or from some element directly there, which is not the case. And then we can say that it is 0. Okay, so D is 0. Now, state space matrices altogether, A here, again, this is the system matrix, and a B here, that is our input matrix, and the C is our output matrix, and there is no D because there is no direct transfer from input to output. Okay, this is then for this example 2.1 about an electric circuit. Let's also check in a mechanical system. We have here two mechanical references. So this is fixed. We have a spring here, a mass in between the damper. We apply a force here, and we have an equilibrium position of that mass in, let's say, steady state condition, and the Y is our vertical position of our mass. So it goes let's say in the vertical down direction, and it goes up, it oscillates. Anyways, it is the action to this force. Now what's saying, it's actually a similar example. Consider the mechanical system, and then the input is the force, and the output is the displacement Y now of that mass, specific, not that of the damper or the, let's say, the spring. Now determine the state space representation of the system where we have the output as our displacement of the mass. That's again important, and we know the input. So we know the input F, we know the output Y, so we can now move on. Again, the solution step by step. In this case, we can set up differential equation using Newton's second law, using this, so the mass times the second derivative of that position or that displacement is equal to the sum of the forces in a vectorial form. Now we have done this many times, so I will just give you the result, but you can also see what's happening. The mass times that mass times the second derivative of time the second derivative of that, I mean that position, displacement, is equal to the force, because that's also in the same direction, but the damper will, let's say, fight back, and also the spring will fight back. So we have the minus b times the first derivative of that position. So that's actually the speed, or the velocity, I must say, minus the k times the displacement. So those are the force equations for the damper and for the spring. Now we have now done the step 1. Now we now define the state variables as the quantities that are differentiated, as we did in the example number 2.1 for our electric circuit. What are those? Now, the state variables that are differentiated in this case is a little bit different, because we have only one element that we talk about. It's not like energy storage elements, in this case like RLC. So we can say there's just displacement and also the derivative of that displacement, so the time derivative of that displacement. So we have now two states variables. In this case, one of them is just itself, the other one is the time derivative of that, and that is also perfectly fine. And so you can see that this is also done in a different way. Now step 3 is define that factor. Now we said the x is now the first state variable, and the second one is now also time derivative of that one. So we have again two elements in that state vector. Now the time derivative of that one is x dot, and you then differentiate this, and you also differentiate this one. That's actually the second derivative. Why we do that? We have also a second derivative in our differential equations using Newton's second law. So we have now also the standard form here. Again, the one dot here for the first derivative, the second dot, two dots here for our second derivative, or 2 times differentiation to the 2 time. Okay, now we have this expression, and we can also divide by m. Then we have this expression. You can see the 1 over m times the force, and then k over m, b over m, all minus signs in front of it, and there's a plus, and we have this expression. Okay, now set up the state-space model. Let's do that. This is the state-space model we know, again, from the previous discussion. And let's then also discuss now what we need to have for A and B and C and D for our matrices. This is the state vector differentiated with respect to time. This is the state vector. This will be a, this will be a B, and here is our input F, because that was the force. So that will be then this 0, 1 minus k over m minus b over m, 0 and 1 over m. Why? Let's check that. Because if I look at this, and if I say the dy dt, that's just itself, and there is no input. So that's actually a first state variable differentiated, and a second state variable differentiated shown here is actually this expression rewritten in this form by divided by m, and we know it has k minus k over m, the first one with a y, and the other one is minus b over m with the first derivative of that y. And it has also input 1 over m, so it's all here. So this is the compact way of writing down this second order differential equation in two first order differential equations. Now the output, we know it is y, so it is straightforward here. Y is equal to y, and 0 times that first derivative of that y. You can also say I want to have that velocity, and that will be, of course, 0 and 1. That is where we then are interested in, but it's not the case here. The output is displacement, no velocity. And let's also look at the state matrix again. The A is this, the B is actually this one in front of that input, and the C is our 1, 0 here, which is actually this one, and there is no direct transfer again, so this D is 0. Okay, so that was our second example. Now let's then also discuss this third topic. Interesting, how we convert now this transfer function to a state space model. Now we start with the phase variables. Now state space representation can be used for simulation of physical systems, and we have many representations. We will discuss this also shortly, and each subsequent state variable is then defined to be the derivative of that previous state variable. Now, differential equation like that in very general form. So we have, let's say, nth order differential equation with some specific input with the coefficient b0. Now, the phase variable choice in this case is then the output yt, because that's the output, and it's n-1 derivatives. That's actually how you choose the state variables mathematically written. Now, if you choose a state variable, let's say xi, and you call it, for example, x1 is y, then x2 is then a time derivative of that one, y. And x3 is then the second derivative of that y, and move on up to the n-1 derivative as shown, as given here. So you can see x1 up to xn, and you go from y to the n-1 derivative. And that's then equation number 1. After differentiating both sides of this expression, you can then have x1 dot, that's this, x2 dot is this one, and up to the x1, xn dot, which is then this expression. Now note where the dot above the x indicates the differentiation with respect to time. This is very short, nice shorthand notation, because we are a little bit tired to write down constantly dy dt and d squared I dt squared, and it's very nice to have this, and we can just move on much faster. Let's also call it equation number 2. Now, substituting if this equation number 2, all the set is included now in here, what you get is the following. You can say x1 is dy dt, but it's actually shown here as x2. x2 differentiated is actually d2 y d squared y d2 dt squared is actually shown here, so it's actually then x3, and moving on in that fashion up to this expression. And you can see this is a more compact way to write it down than this and this in, let's say, time derivative expressions, and we can now write it down also compactly in our matrix vector form. Now this is equation number 3 also. And you can then set our differential equation here in terms of the rest of the values which are in the state variables, including our input. So that's also one of the advantages. Now, moving on, let's also look at the vector matrix form. We also discussed this. So we have now the A and the B, which are the system matrix, and also the input matrix. X is our state vector, U is the input, and x dot is the time derivative of that state vector. These are the phase variables, so we already discussed this. And this is now the expanded version of that one. So this here, x dot, is our state variable derivative. So each state vector element is time derivative, taken the time differentiated. It's all shown here. It is just a state vector in green here. It's all here. And there's all the u and also the u. You can of course have 2 or 3 inputs depending on your system, and in this case we discuss only one input and one output. This can be then written in this form, in very general form, and that is just for phase variable format. We also discuss later the other representations like control canonical or observer canonical forms. And this is all what you have, so 0, 0, 0 up to the final one, which is B0, which is our input coefficient. It's also shown here. So this whole thing here is actually given as a matrix expression here. And you can see the coefficient minus A0, minus A1, up to minus A and 1, all here. So the phase variables choice, again, as we said, the y, and it's the n-1 derivatives as the state variables. And this is our output, again, the C for our output matrix, and D our direct transfer from the U. And it's now expanded also here. So you start always with 1 and up, and then all of them, the rest of them are zeros. And we have here the state vector again. Now let's also look at an example that will be, of course, easier to grasp this material. Now we go now from a transfer function to state space form. In this case, I discuss only the phase variable form because we have infinite many forms of state space representations. This is the transfer function we will discuss here. This is the third order system, so 10 over s cubed plus 6s squared plus 21s plus 5. Now determine the state space representation in phase variable form for this transfer function. How do we start? Now it has a constant term in the numerator, so we'll discuss this shortly why this is important. Let's go to the solutions. Obtain the differential equation from this transfer function. Now we have this given y over u in Laplace domain, shown here again. Now let's then cross multiply, so y times the denominator is equal to the 10 times u, shown here. Now we go to the time domain representation. Of course, assuming all the initial conditions are 0. So we have now third derivative here, second derivative, the first and the 0 derivative of y's here, and we have only, let's say, the constant times the u, which is now here just itself without any differentiation. Now choose the state variables. We said we need to choose the state variables which are then differentiated. In this case it is this y, and it's again differentiated, So we have x1 is y, x2 is then the time derivative of that y again, which is y dot. x3 is then again the time derivative of that one, which is then y double dot. These are the three state variables. Now differentiating both sides of the state variables here, we get x1 dot, which is y dot, which is x2. So actually, and x2 dot, which is y double dot, and that will be the x3. And that will be then, you will then move on like that. So this is then the, let's say again, the differential equation. We have here the 3 dots on top of that y, and again 6 times double dot, y double dot, and plus 21 y dot plus y, 5y is equal to 10u. Again, what we have before here. Now we can express this y, 3 dots on top of it, is equal to minus 6y double dot minus 21 y dot minus 5y plus 10u. Just rewriting this and keeping only the highest derivative term on the left side. Then we can also say this is this, so it's the exact same for x3 dot. Okay, now expressions for the state variables and the output. This is x1, so x1 dot is equal to x2. So this x1 is y dot, x1 dot is y dot, and y dot is x2. In simple form, x2 dot is x3y, because x2 dot is y double dot, which is here. In a similar form, we know that x3 dot is this, so that goes here. But we also know that y double dot is x3 dot, x2 dot, and that is also equal to x3. So you can just write down actually everything for this expression and then collect the terms together, and we have this expression. And we know that the output was x1. Okay. In this case, we choose that, actually. This is our output. Now let's then move on. Now this is what we have, and this is also a diagram to represent these state variables in our output. So what you see is the following. We have the output y, and we have also the u that goes in 10 times. This will be what we say. And then we go to the x3 dot. Now let's see what's happening here. We have then 6 times x3, which is actually shown here. So x3 dot integrated, so you will lose your differentiation. x3 times 6 minus that will go here, so it's correct. You will see x2 here times 21 minus actually 21, and that goes also here. And you have also minus 5 times x1, which is actually shown here, also with a minus sign. And we have here plus 10u, already said that. And we have x1 as an output, which is actually directly your output here. So you see in this form the following format. We have the x3 dot, which is our output, I mean the state variable, which is the final one, the third one. And then we have the second term here, which is the non-differentiated form of that x3, and then x2 and x1. So you actually put in x1, x2, and x3 here in between the integral terms, and then also an integral term here, and then put also there the x3 dot, and you just place these blocks together, and that is the phase variable configuration. And this 10 is due to that 10 in the numerator. We have a constant term there. Okay, now vector matrix form then here, which is this, and that will be then converted to this one. And you can see here 0, 1, 0, 0, 0, 1, that is standard. But this one, minus 5, minus 21, and minus 6 actually is coming from this denominator. So 5, 21, and 6, you actually put a minus sign in front of that, and you do that in a reverse way here. So minus 5, minus 21, and minus 6. This is all 0, 0, 10. So let's actually do that 10. You can also do that 0, 0, 1, but then you need to change the output matrix. And that is actually shown here. The C is 1, 0, 0. You can also have 10, 0, 0. Then you have 0, 0, 1 here. And we don't have direct transfer. That's actually D is 0. So the state space matrices all here given. All right, now we have this example number 3.1. Let's also look at the situation in the MATLAB code and also the MATLAB command window, because I have also simulated this. This is what we had. We have discussed this, and these are the matrices, and this is our script to do this analysis. So we have the transfer function here. I also, let's say, made an expression for the numerator coefficients 0, 0, 0, 10. That means the third order 0, second order 0, first order 0, and the zeroth order is 10. That's actually shown here. And for this expression, I have 1, 6, 25, and 5 as the coefficients. That's actually shown here. The state space model matrices now are the phase variable form. These are given here. We have discussed this. It's all shown here. And I have also several other expressions here to go from, let's say, these matrices to the state space representation, and from there also to the transfer function to check that this is indeed correct. So I need to check that these 4 matrices are indeed producing this transfer function. Now let's run this. What's happening? You can see here I've run this state space example 3.1. That SS means actually state space representation of these 4 matrices. You can see also the matrices here. So this is actually what I have just inserted in that script. So this is actually my input, and this is a continuous time state space model. And if I do now GTF, which is the transfer function, just my name, and TF is the command in the MATLAB, for that system here, I defined here, I will get 10 over exactly as I have here. There's one interesting thing here. If I now, for example, want to go from the transfer function to state space, so actually this from here to there, directly using MATLAB, I get this, which is different. You can see it is minus 6, minus 21, and minus 5. Sort of flip this here and then move up, and then that also the orientation is different. And the B has also a little bit different, let's say, orientation. And D is 0. But why is this happening? There is the following reason for that. This is given, the MATLAB produces actually this TF to SS, so converting from transfer function to state space, it always gives that in the controller's canonical form, which is a different one. And that is perfectly fine. But you need to be aware of that, of course. If you work with phase variables, then converting that, your transfer function, to using MATLAB to a state space expression or state space form, don't get surprised, for example, if you get a different matrices. It's not wrong that you have this, it's just a different representation. So A, B, D, C, D with this one will produce always, in this case, the controller canonical form in MATLAB. So it is fine, we will see that later. Now let's also look at the 3.2, which is another one, and we have exact same denominator. Why I have now placed this numerator in a different form. So we have now polynomial of a higher order than 0 in the numerator. So we have a second order polynomial here. Again, separate this. In this case, we need to separate the G in 2 blocks in cascade. So we have this. So we have G, U comes in, Y comes out, and I have to separate this in G1 and G2. That is one of the ways to do that. And first block contains a denominator, this, so 1 over that. And the second block contains only the numerator. So this is what we had, so expanded here. And this will be then this. So we have 1 over that denominator. And internal phase variables will be then x2 and x3. So x1 is actually the in between the variable. And then you have only that block, which is then our numerator, and you go to y. So you have the u up to y, in between we have an x1. That's the change between the example number 3.1. So how do we work it out? Now let's look at it. Vector matrix form, again, is the same thing. This is exact same, that doesn't change, system matrix. This is 0, 0, 1, that does change, it was 0, 0, 10, so we don't have 10 anymore here, we have actually 1, so this is only for, let's say, the G1 term. Now the C will now have that 4, 7, and 8. Now we can see it is 4, 7, and 8 in the reversed form. We also don't have that direct transfer, so it is also given here as 0. So that is also the standard way to doing that. So 5 here as minus 5, 21 as minus 21, 6 as minus 6, and this is standard, so you just actually copy that if you use phase variable form. This is 0, 0, 1. You copy now also this one, 8 is here, the first one, so you can actually go from right to left, 7 here, and 4 there. And again, you have your vector, and you also don't have any direct transfer. Now state spaces matrices are shown here again. So B is 0, 0, 1 here, and C is now different, and D is 0. And this is what we had, and this is now our diagram. This, let's say, our signal flow diagram. Remember that we had before this, and then we had the output there. Now we have also that the output needs to be also after that x1. So x1 must be multiplied by 8, and then also y, but it also has to be differentiated, and then times 7. That's actually shown here. So you go actually so from this to that, you integrate, but from this point to the left side, you actually go then in differentiation. So differentiate that. That's actually shown here, and then you do multiple times 7, and you come actually the output. In a similar form, you need to differentiate now twice, so s squared, and then times 4. Again the x1, so x1 first derivative, second derivative, times 4, added to the output, and you have actually your result. So these 3 blocks, including that operation here, is that addition of that numerator polynomial, and the rest is the exact same as in example number 3.1. Okay, that's now the expression also given in the signal flow diagram. Alright, let's also check the MATLAB code for this one, also the command window results. Okay, this is the expression we had, and these are the matrices. This is the script I have developed here. Again, the matrices here, and also the transfer function just to check this. Now let's run this example number 3.2. You can again see all the matrices here. We also do that again for TF using this state space model. You get a transfer function exact same as we have. So our A, B, C, D are correct because we get exact same transfer function as we started. Again, we check the let's say the transfer function to state space conversion of MATLAB. So the num G and then G is actually the numerator of the G, and the denominator of the G I also place it here, so 0, 4, 7, 8, 0 because there is no third order term here, and then 4, 7, 8 for the coefficient, and the rest is exact same as before. You get this, and you're gonna again see that this minus 6, minus 21, and minus 5 is flipped here and placed in the first row, and also these are given here in a different form. But the rest are exact, sort of exact same. Again, 0, 0, 1 is converted to 1, 0, 0, and this is again flipped, and there is no D here. So it is again the controller canonical form here when you apply this formula in MATLAB. That is, of course, what you need to consider. Okay, let's move on to another topic, which is the conversion of state space model to a transfer function, also very important. So state and output equations. This is the equation here, and the Laplace transform for that will give you, because this is a time derivative of that one, will give you s times this x in terms of the s parameter, and all of them will be also given in the s parameter. There's only one derivative here, so there's only s here. Now, if I now solve for x, that means replace this ax to the left side, and we have this one. Collect them together. Of course, we work with vectors and matrices, so we can not do s minus a, so we need to do s times the I, which is our identity matrix. That is sort of the matrix vector world, times the x outside is equal to b u, all of them in the s variables. Now I have this. If I now go from here to there, I can now say the left side here of this x, I need to take the inverse of that one. It means also the left side of this one, so si minus a inverse times the bu. Now that is our first equation, and we have now expressed that x in terms of the rest of the variables. Now substitute that 1 into the expression for y. Where is the expression for y? Is here. So let's do that. So we place the x in here, so c times the whole thing here for equation number 1. What you see now, we can of course take that u out, so we have the c times the si minus a, and then the inverse of that one, times b plus d, and the whole thing times u. Now we know u is our input and y is our output, so we need to have an output over input. So if u and y are scalars, for example, could be the case, you don't have to be a vector, then we can say y over u, which is our transfer function, let's say the total transfer function or some transfer function, is given by this expression. It's interesting, we need all the matrices and also some operation using that matrix A and then si minus a, and we need to take the inverse. So we need several steps to do that. But this is the formula going from the state space to the transfer function. So in summary, this will be converted to that if you work out this expression. Now let's do that in an example. 4.1, from state space to transfer function. This is the state space. It's a second order system, so let's start with the easy one. We have the matrix A and a B and the C here. There's no D here, so let's determine the state space matrices. A is just this one. There is B here, and there's also C. D is 0. So it's actually scalar value. So use the formula to convert now this to the transfer function. This is what we have. And we know that this must be then given by this expression. So all of this converted to this one. So I need to do several things step by step. First, si minus a, and then the inverse of that one, and then multiply by b, and then c, and then plus d. So I will do that. So first, si minus a. In this case, we have a second order system, so 2 by 2. Your identity matrix will be also second order, so identity matrix have actually ones in a diagonal from left top to right bottom, and the rest are just zeros. Will be multiplied by s as our Laplace transform parameter, minus our a. Now let's substitute s here. So as s, work this matrix, you will get this s plus 6 minus minus 6 and s plus minus minus 2. That is actually shown here. The rest are minus 7 and minus 1. This is now that thing here in the parentheses. Now we need to move on to the inverse. Inverse of a 2 by 2 matrix is quite easy to do. It is 1 over that determinant of this one. So the determinant of that one. So we need to determine that given by that, and we need to flip this and this. So we need to change the location of the position of these. S plus 6 goes here and s plus 2 goes there, and we need to change the sign of these two elements. That's actually the formula. You can see that will be plus 1 and plus 7, and these are replaced. I mean changed here, the location. Now what is then the determinant of that si minus a? That's quite easy. You need to of course look at this one or that one. Sometimes people make mistake by looking at this. So this is this times that, so actually s plus 6 times x plus 2 minus 7 times minus 1. So I will write it down here, it's shown here. So if you work it out, you will get s squared plus 8s plus 5. Okay, that's actually coming here, and the rest is our expression for the matrix here. Now we have this part of our expression. This is actually one of the hardest parts. Now we need to multiply it by c or b, doesn't matter where you start, so I just choose c. So 2 and 1, and then this is just a factor, let's say in a horizontal form, and you multiply that by this expression. And how to do that? You actually do 2 times the s plus 2, and then 1 times 7. So 2 times s, 2 times 2, because there are 2 terms here, and then plus 1 times 7, so you will get 11, because 7 plus 2 times 2 is 4, and 7 plus 4 is 11, and 2s. In similar form, you also do that for 1 and s plus 6, so 2 times 1, and 1 times s, and 1 times 6, so you will get s plus 8. You will have again that 1 over s squared plus 8s plus 5 in front of it. Now we need to do the next step is just times b. Let's also do that. So we are really close. 4 and 5 here. Again, multiplying by the the rules we know from matrices. We'll now have 13s plus 84. How we do that? 2s plus 11 times 4 plus s plus 8 times 5. And you work it out, you will get this straightforward, I think. And now we need to also do plus d, but there is no d, which is 0, so this is just what it is. And this also our transfer function, so you can move this up to the numerator. And this is our transfer function. So we have this 13s plus 84 over s squared plus 8s plus 5. So this will be our transfer function from this state space representation. What you now can do for yourself is, as we did in the previous examples, in this video, you can say, okay, I will now take this and again use then the conversion to this state space and see if this is really correct. Or you go from these 3 matrices given here, or the 4 matrices, and then determine the transfer function and check that this is indeed correct, which is true. Okay, let's also look at a more complex expression, which is a third order system. Shown here. This is a third order, and I will go a little bit faster in this case. Again, determine the state space matrices, A, the B, and the C. There is no D. Okay. Now use the formula to convert the transfer function from this form to that. Again, we need to do a lot of steps. In this case, it's a third order, so it's quite lengthy. Since we know what we need to do from the example number 4.1, I will go a little bit fast and also skip some steps. So this is the third order system. Again, take them together, work this out, you will get this. Now the inverse of that expression is a little bit different, because this is now a third order system. We don't have that easy formula anymore. It is still 1 over the determinant of that expression, but now we need to have an adjoint of that as I minus A, which is a huge matrix, again 3 by 3, but there will be a lot of calculations. I will just give you the result here, and that is our determinant value of this one. This is quite easy to do, but this will take some time. And you can check this for yourself. It is not that difficult, but it is kind of time consuming, so I will just leave the result. You can always do that in MATLAB too. Now then we get the following, because once you have this and also have this and multiply by C, and then after that whole thing by B and add the D, which is in this case again 0, you will get this one. Now what you again can do now is get this 3 or 4 matrices, again set that in a state space form, then go back to the continue to the transfer function format, and check that this is indeed correct, so that we get from this transfer function. Okay. All right. Let's also look at the final topic, which is our state space representation forms. Now we know we have this state space representation in a general form. So we have the x dot is equal to ax plus bu, and our y is our output cx plus du. If this is the general expression for our, let's say, a third order system with a third order polynomial and a second order polynomial in the numerator and a third order in the denominator, we have following forms. So the vector matrix form here can be given in this form for the third order system. So the time derivative of the state vector is equal to a times the state vector plus b times the input. For the output is this, so the output is then the c, which is our output matrix, times the state vector plus d times the input u. Now, we have dealt so far with the phase variables. We have of course seen that it is in a different form when we use the MATLAB. So we get in the controller canonical form. Now this is the general formula for third order systems. We see again the same format, let's say the template in the A matrix, and we see minus A0, minus A1 and minus A2. So actually you just pick these three coefficients and you place it here in this format with a minus sign in front. And this will be 0, 0, 1, that is also a standard. Now for the y, which is the C matrix here, you will get actually values from the numerator, which is again in the reverse order, so B0, B1 and B2. So if this is just 10, what we had before, this is just 10, 0, 0. Or you do this 1, 0, 0, and you will do this 0, 0, 1. That is also possible. But it is just only the phase variable form, one of the many other representation forms. You can also have the controller canonical form, what actually MATLAB produces, which is given by this expression. And we saw that is indeed a template here. So the second and the third row is always this, but the first row is actually given by minus A2, minus A1 and minus A0. So you'll actually take this, this and this, you put a minus sign in front and place it here, the three coefficients. But this time it is 1, 0, 0 for the B vector or the matrix. And for the output, it is similar to that one again, reversed, B2, B1 and B0. It is actually a little bit easier, I think, to control the canonical form. You can just directly take it and you don't have to reverse it, etc. That's maybe also one of the reasons to have that and what the choice for the form in MATLAB. Another reason for that is a little bit beside this video discussion, that the controller design and state space is also really important, so this is also a handy way to have it already in that form. Okay, we also have the observer canonical form, because in the state space control design we have the control law design, also the observer or the estimator design, so we have also the representation for that. And how is that looking like? It's again a quite different form. So we see again minus A2, minus A1, minus A0, again a template here. So you pick just from this transfer function the right coefficients. And here you now have B2, B1, B0, so different. It's not just 1, 0, 0. But the output is just 1, 0, 0. So that is, in this case, the observer canonical form or estimator canonical form. Okay, now we have seen three representations. It is not the only three. We have many, many, many more. And I will show you also that here. So this is again our second order system, let's say. And this is now an example of a second order system. And this is what we have used so far. So phase variable, we have this transfer function. And what we see is 24 and 10. So it will be minus 24 and 10 here. And 0, 1 and 3 and 1 in reverse case here. That's the phase variable. And this is the signal flow diagram going from the reference to the output C. In this case it is U as input and Y as output, but in this case it is R and C given is actually the same thing here. So C is the Y and the U is the R here. Now the controller canonical form, let's check that. This is minus 10 and minus 24 here, and a 1, 0. And 1, 0 here for the B, and 1, 3 actually for the controller canonical form, and similar form for the observer. So we can see that we have the three forms we have discussed using also the second order system. But as said before, there are many, 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 many more state space representation, actually infinite representations. And another two representations sometimes used are the parallel and the cascade. So again, this thing here, expression, transfer function, will be just converted to using the partial fraction expansion into two fractions, and then convert back to another state space representation. Or it can be a cascade of two first order systems which are multiplied, and then that will be again converted to another state space representation. So you can see these 5 state space representations all different, but it has the same transfer function, which is of course very important. Okay, now let's look at an example of a third order system here, and then determine the phase variables, the controller phase variable form, the controller canonical form, and also the observer canonical form, and then discuss this example also. Now we have this is then the general third order expression, again the polynomial for the denominator and the numerator. This is what we have. We know that for the phase variables, and this is for the input, and for this for the output. Now let's just substitute everything. We have the -7, -10, and -5 from this. You can see it, -7, -5, -10, and -5. The rest is just a template, and 0, 0, 1. Just we take this and we look at the coefficients from this transfer function. So you compare this G in that red region with that G in the blue region. That would be B0, B1, and B2. What is the B0? 9, 4, and 6. So you will get 9, 4, and 6. And that's actually shown here. That's it actually for the phase variable. Let's now look at the canonical form, controller canonical form. This is just this is the template. This is exact same. So I need the A2, A1, and A0, put a -9 in front of it, and also for this one. And this is the result. This is actually much easier to solve, because we can see it is -5, -10, and -7. Directly in 6, 4, 9, that goes much faster. This is only 1, 0, 0, not 0, 0, 1. Okay, looking to the final one, which is observer canonical form. Again, we just use the template, moving to the values here, just template here, template there, and exactly as we did before. Okay, now let's then get them together in summary. This is what we had. This is the state space model, and this is now the representation: phase variable, controller canonical form, and observer canonical form. I have discussed these 3 specifically because these 3 are most often used in the state space controller design. And you can see also differences in the A matrices and the representation, also the B, and also the C, and also the D. In this case, these are all assumed as 0. There is no direct transfer. These are the formulas. Now, if I now use this example, I will get from here, because that's actually the general form, these values, and this is actually all the summary. So you can see the change or the differences between the different state space representations. All right, this is for this example 5.1, and also concludes this whole discussion about the state space modeling using different representations, and also some examples using the RLC circuit and also the mechanical systems. I hope this gives you a general idea why we do this state space modeling. It helps actually also in our design to calculate and also proceed in the controller design in a much efficient way. That's also the reason for the discussion of this state space modeling. In a classical way, we have only one feedback loop. In the state space expressions or state space modeling, we have multiple feedback loops, which allows you also more freedom, so you can also assign or place your poles at any location, which is not possible if you do the classical controller design. If you have any questions about this set of examples and a discussion, please let me know and I will try to answer them in this video as soon as possible. See you next time in the subsequent videos about this topic, about a design using state space modeling.